Okay, can everyone hear me? All right, cool. So today, instead of talking about the moon, we'll be talking about other airless bodies. So I hope everyone's excited for a little switch up. I want to specifically shout out my advisor, Dr. Carrie Donaldson-Hanna, as well as our collaborator, Dr. Jeffrey Gillies-Davis here at WashU. So why do we care about any of this that I'm going to talk about today? So carbon is hypothesized to be present as a darkening agent on the surface of Mercury from excavations of a theorized graphite flotation crust. And this carbon could exist in concentrations of up to 5 weight% within Mercury's low reflectance material. So the question that we're asking is, can this carbon also be a component in nanophase or microphase space weathering products? So we aim to simulate the effects of space weathering on Mercury and regolith analogs that contain little to no iron. The silicates that we have are mixed with various carbon-bearing opaques to characterize how different forms of carbon will also impact the results of simulated space weathering experiments, because as of right now, the choice of carbon is sometimes all over the board, kind of willy-nilly. So here's our sample suite. We have 3 silicates, San Carlos olivine, as well as synthetic forsterite and synthetic instatite. We also have 3 opaques. Today I'll be showing you results from our anthracitic coal and carbon black mixtures, and in the future we'll be using graphite. Particle size is very small for all of these, so everything is less than 80 microns. So first thing, some spectra to show you. I'll go through the plots first, and they'll stay the same throughout the presentation. So on the x-axis, you're going to be seeing wavelength in microns or wave number in inverse centimeters. And on the y, depending on the region of the wavelength region that we're looking at, you'll see reflectance on the y, or you'll see 1 minus reflectance on the y for the mid-infrared. So as you can see, the instatite and forsterite are truly iron-free. There is no 1 micron band due to iron, which is really cool. And on the right, for the mid-infrared spectra, you'll be able to see that the forsterite and the San Carlos olivine have features in similar positions, which means that these synthetics are actually pretty good analogs for our work. So we're really excited about that. Here are our opaque end members. These spectra were taken at Relab, and it's worth noting that these 2 different carbonaceous opaques have different slopes. So that's going to definitely, in the visible near infrared, so that will impact the results of our work. So to do this experiment, or this series of experiments, we're using the Washington University Laser Space Weathering Laboratory. It uses 2 continuum Suralite I-20 neodymium YAG lasers to simulate micrometeorite bombardment. There's a long pulse laser that generates the melt portion of a micrometeorite impact, and a short pulse laser that generates the vapor part of the impact. The spot size on the sample is around 300 microns, and we get around 20 shots per second on the sample. We irradiate at a pressure of around 10 to the minus 7 torr, and it goes up to about 10 to the minus 5 as we're radiating, then drops back down really quickly. And one really cool fact about this setup is that you can generate agglutinates with it, which is different from a lot of other laser space weathering setups. So we irradiate our samples for 32 minutes, and that is how long it takes to reach the maximum optical maturity of olivine with this sample. So it's a measure of albedo. After the first 16 minutes, we'll break vacuum and mix the sample just to make sure that everything is being irradiated evenly, and then we'll go forward from there. So 2 motors help move this mirror that's over the sample chamber to raster the beam over the sample. In the middle there, you can see the sample itself in its little sample cup. And there's also a restrictor funnel that we place over the sample in order to keep the sample from flying everywhere inside the chamber, but there is still some loss of sample. So results, I would show you some SEM images that are really cool and show you all of this melt and really awesome things that are proof of the physical weathering, but we only have time for spectra today. So we'll get into our visible to near infrared spectra first, the standard space weathering picture. So we see spectral reddening for all of our samples, as well as a near complete removal of the 1 micron feature for olivine. And we also see a decrease in reflectance for most samples. So we'll have the forsterite and the instatite shown first. The little gray spectrum that you see at the top is the spectral unreflectance standard, just to show you how bright white these materials are starting out as. The black spectra are the spectra or the materials before they have been irradiated, and the colorful spectra will be the material after it has been irradiated. Just past 2 microns, you can see a little gray bar that's standing vertically there. That's just a feature due to spectralon, so just don't pay attention to anything that you see there. It's not special or notable. You can also see 2 little gray dots on the spectra, and those are the regions between which we calculated spectral slope, or that delta M shown down at the bottom of the screen. This is the spectrum of our San Carlos olivine before and after irradiation. You can see this material is getting really dark. And again, we're having that almost complete removal of the 1 micron feature. Here are the spectra for our mixtures of olivine and 5-weight% of carbon black, as well as olivine and 5-weight% of anthracitic coal. First, I want to draw everyone's attention to the reflectance. These are really dark. They are very, very dark materials. And of special interest on the left, this is the only spectrum where not the whole spectrum itself, but the spectral slope calculated between these 2 points got bluer. So this is where we're hearkening back to that. Your choice of carbon and your choice of analog is really going to matter for these type of carbonaceous experiments. We'll get to some mid-infrared spectra as well. So these are shown in 1- reflectance space, and we see some minor changes, but there's nothing stark that we're going to expect to change under ambient conditions. So here we have the forsterite and the instatite. The same thing goes when it comes to the colors here. So the black spectrum is before irradiation and the colorful spectrum is after. You can see that I have marked the Christensen feature position with those dotted lines shown there, and the color corresponds to the proper spectrum. One thing to note here, the instatite spectrum doesn't change too much, but the forsterite spectrum gets that funny little blip change in the shape of the Christensen feature. This is our spectrum of San Carlos olivine. Sort of flip through these. The carbon black on the left here, the carbon black mixture, and then the olivine and anthracitic coal mixture here on the right. So now we can get into the fun stuff, the discussion and talking about future work. So clearly, we saw physical changes. That's the first thing to note in our SEM images. And we also saw visual darkening of all of our samples as well, even the ones that had no iron in them whatsoever, or carbon. We also clearly see spectral changes. So we're seeing changes in spectral slope in the visible to near infrared and some changes in feature shape in the mid-infrared. We really want to point out that the analog choice matters. So the form of carbon that we're using impacts spectral slopes and features. And it's also worth noting that our iron-free synthetic minerals behave well spectrally and they look the way that they're supposed to look. So these are likely relevant results. In the future, we expect to see more spectral changes. So hopefully we can put these materials under simulated Mercurian conditions or emissivity so that we can see shifts in the Christensen feature position in the mid-infrared. We also will weather more mixtures. So we'll mix and weather our carbonaceous opaques with our forsterite and instatite samples as well, so that they're pretty relevant for Mercury in particular. And in the future, we might also vary the weight % of carbon that we use. So our conclusion, you don't need nanophase iron to see the effects of space weathering. So after performing our simulated micrometeorite bombardment on our samples, we saw physical changes in all silicates and the silicate carbon mixtures. We also saw spectral changes, including darkening, reddening, changes in slope, and changes in feature shape. Our current work, we're working on using transmission electron microscopy and electron energy loss spectroscopy to search for the formation of nanophase opaques, hopefully nanophase carbon. And in the future work, we'd like to play with variables like looking at how solar wind ions may affect our samples instead of simulated micrometeorites, and then also looking into how using pressed pellets instead of loose powders may impact the spectral features we see. So, thank you.
I think we have time for one question.
Very nice talk. I'm really curious about the shift in spectral slope between the coal and the carbon black. Do you have any thoughts on what might be causing that difference in slope in the visible near infrared spectra?
I am not quite sure what's causing the difference because it's really hard to figure out what the carbon black itself is actually made out of. It's just like something that people are like, we combusted some stuff, but it's really often used in experiments like these. So the carbon black is nanometer scale, and the anthracitic coal is, I think, at least under 45, but it's very, very small. So.